Okay, welcome. So we're going to be working on continuing our work on thermodynamics. The two topics we're going to cover today are going to be heat conduction and thermal expansion. Now these are related, um, but I just want to give you sort of a heads up about what heat conduction is and what thermal expansion is. Heat conduction is how heat moves from one object or one system to another. It doesn't have to just be an object. It can be any place that kind of stores thermal energy from one system to another. And then thermal expansion is what happens to a system when its temperature changes. Okay, so what you can think about it this way is the major topic we've covered is heat capacity. That's how does heat affect temperature. And then we're going to talk about heat conduction. How does heat flow from one reservoir to another? And then thermal expansion. How does changing temperature affect an object? Okay. Or again, a system. So that's generally the way we're going to look at it. Now, heat conduction is a category or is a subcategory of the larger overarching category of heat transfer. And there are three main methods of heat transfer that I do at least want you to know about. We're really only going to talk about conduction. That's the first one. Now, heat conduction, this is heat transfer through direct contact. Okay. So the idea here, so through direct contact. The idea here is like if you're using with heating air, it's a little bit more nebulous, but a good example would be you're using your stove to heat up a pan that has food in it. Okay, so basically what you're doing is you're conducting heat from the stove through the pan into the food. All right, and that's basically what heat conduction is. And anytime two objects are exchange heat through direct contact, that's going to be heat conduction, but there does need to be direct contact. And basically the idea is that heat will spontaneously flow from high temperature to low temperature. That is actually one of the laws of thermodynamics. We'll talk about that in the next lecture, but that's the main idea behind heat conduction. And it's the main one we're going to talk about. Convection, I want to talk about briefly, and then we won't come back to this. Basically, this is heat transfer through movement of material. Now, the where you've probably heard this is in the term convection oven. And the way a convection oven differs from a normal oven, effectively what's going on in a normal oven is you get the heating element really hot. That heat conducts to the air, which then in turn conducts to the food. Okay, so it's all basically through conduction through different materials. With a convection oven, what's going on is you're taking in little bits of air into a specific region, you're heating them up, and then you're blowing the hot air out into the other system and you're circulating the hot air. So basically, you're heating up the entire system by forcing hot air into it, okay? And that's kind of what's different. Now, another area where this comes up would be like cooling off your food by blowing on it. Your food will naturally cool off, but it's faster when you blow on it. And the reason why that's the case is basically when your food just naturally cools off if there's no moving air, heat conducts from the food to the air, and then the air gradually it diffuses, but it also conducts to air further away. What you're doing if you're blowing on it, you're taking the hot air that's right next to the food and you're blowing that away and forcing cold air in. So you're removing heat through convection in that case. Convection plays a major role in weather patterns. You have both hot air and hot water currents in the oceans and cold currents that move material around, and these are responsible for large exchanges of heat in the global system. Now, the third method of heat transfer is radiation. And basically what radiation is heat transfer through light. That's really when the term radiation is used in physics, it generally just means light. There are a few contexts where we're talking about radioactive particles, where we don't necessarily just mean light. We were talking about the particle, but in general, the term radiation just refers to light. And anything that is not absolute zero, it actually it glows and it emits some light. So basically, it glows in some in it when we say something glows, basically what we mean is it emits its own light. And you basically do this by virtue of the fact that you are not at absolute zero. Now, our eyes cannot detect the glow that human beings emit, but we do emit a glow. And you've probably heard of this, infrared. And this is why infrared goggles work. Humans basically glow infrared light. Okay. Things that get hotter, they start glowing visible light. So an example of this should be you heat up a piece of metal, it starts to glow in the visible light. So it needs to be quite hot to glow in the visible spectrum. But that's basically what's going on. This is also how incandescent light bulbs generate their light. I mean, that was kind of the trick to it. How do you get the thing hot enough to glow that it emits light? But without the thing burning out, and that was a problem that basically Edison had to overcome. But that's basically what we're talking about when we're talking about radiation. Radiation is the primary mechanism of heat transfer through space. So there's no absent space is so big that for the most part things they don't come into direct contact very often. When they do, you definitely get heat transfer. You actually get quite a lot of it. You get quite a lot of mechanical energy converted to heat. But for the most part, energy is transferred and heat is transferred between objects through radiation. So there's no material in between the sun and the earth to transfer its heat via convection. We're not in contact with it, so it's not via conduction. So all that heat gets transferred through radiation. Now, to think of, if we were to study convection, basically what that would be a combination of a study of fluids and fluid mechanics, fluid motion, and a study of thermodynamics. To study radiation, that would be a combination of electromagnetism, electromagnetic radiation, and thermodynamics. So understanding these mechanisms of heat transfer, they do start to touch on sort of not necessarily interdisciplinary, but cross topic, and the way the different topics interact with one another in physics. And again, a little bit beyond the scope of this course, but we will be talking about conduction. Okay. And the idea here, just make sure we know that it's heat conduction. It is contrasted with electrical conduction, and it turns out that they are quite similar. Instead of having current flow, we're having heat flow, but it turns out there are a lot of the physics is the same. So the idea behind heat conduction is Q is going to be the amount of heat that flows when two systems are brought in contact, or say brought into direct contact. Okay. So the idea is that basically you bring these two systems into direct contact. Again, we think about temperature as being proportional to the internal kinetic energy. One system has a lot more kinetic energy. And basically the internal molecules vibrating at the barrier, they're what causes the vibration in the cooler system to start vibrating more. And that net effect is a transfer of heat energy. Okay. Now, the thing that this depends on, the amount of heat that get transferred depends on a couple of things. I'll tell you what I would suggest you do, pause and try and come up with, there are 5 things that really matter. See if you can come up with just a few. Go ahead and pause it and check that out. But moving on, the first one is going to be symbol is area, A, and it's the contact area. So how much contact is there between these two systems? So you can imagine this, that you that you tend to lose a lot of heat through windows. Your windows tend to conduct heat better, and doors tend to conduct heat better than the insulated walls. So the idea is that if you shrunk down the number of windows or made them smaller, you would use less heat or lose less heat. That's not That's not it's not so hard to believe. Another thing that is relevant is the time of contact. So in the case of like a house in cold, you know, you wait, you kind of, it's perpetually in contact. You can't really break the contact. But if you're talking about heat conducting from a stove through a pan into some food, then the main then you know you get more heat into the food if you leave it in contact longer. You cook it longer, you get more heat into the food. The other thing that another thing that is a big deal is delta T. And this is the hot temperature minus the low temperature, the high temperature minus the low temperature. Um, and basically that's the difference in temperatures. Now, the idea is that no heat will flow if these two things are already in the same temperature. That is actually also one of the laws of thermodynamics. We're not going to get into that today. Talk about that in the next lecture. But if you have no difference in temperature, then no heat will flow. And more heat flows, the greater that difference of temperature is. Okay. Now, one other thing, this one helps if you go back to insulation. D is the symbol we're going to use, and this is the distance the heat must travel. The heat must travel. All right. Now, I'm not giving units for all of these, but they are SI, so we'll get to that in a minute. Now, there is one other thing that matters, and this is I'll give the symbol, the material heat is moving through. Okay. And this is just like in electronics. Some materials they insulate well, some materials conduct well. Um, Now in electronics, you typically you kind of make the assumption it's either a conductor or an insulator. Now, in a certain sense, that's not a yes/no question. It kind of is, but but really, if you get more fine grained about it, you can talk about how everything sort of conducts. You just talk about how well. And similar with heat. Everything will conduct heat, but some things conduct it really well, and some things conduct it really poorly. Now, the symbol we're going to use for that is a lowercase k. It's another symbol that gets used a lot for a number of things, even in thermodynamics. And this is what we call the thermal conductivity of the material. So it's a measure of how thermally conductive a material is. How well, what is the means by which this material conducts heat, or how well does it conduct heat? Okay, so thermal conductivity of material. Now, what we have here is these are the five factors, but we still need a formula. So the heat itself is going to depend directly on a couple of different things. One, it's going to depend directly on the thermal conductivity. That's just a constant that we define for different materials. I'll also say the thermal conductivities you might need to look at. This would be in a table, and I think it's 14.5. I'll check that really quickly just to make sure. I think it's 14.5. Yeah, it's 14.5. You can look up thermal conductivities in 14.5. But then it also depends on the area. A larger area means more heat can conduct through it. It will depend directly on the change in temperature, not the change, but the difference between the two temperatures. You can think about that as a change in temperature. And it'll depend directly on the time. Now, it will actually depend inversely on the distance. So the further you make the heat travel, the less likely the heat is going to be able to kind of make it through. So this is why you increase the thickness of your insulation. The heat has to travel further through the insulation. It reduces the amount of heat lost. Now, typically, this is represented as a rate of heat flow. And basically what this means is you have Q over T instead of Q. So we tend to talk about how much heat per unit time rather than how much heat. overall. You can be asked questions, but the equation is typically written like this. So as a reminder, heat is a unit of energy. So basically, it's represented as a power, sort of a power loss due to heat, or the sort of radiative power of the system, the or the conductive power of the system. Like that would be a unit of watts on the left side now. And basically, instead of having the T on the right, you just divide both sides by T. So this is just equal to K A delta temperature all over D. Okay. And for the most part, the difficult portion of problems will be identifying each one of those. I do want to quickly run through the units. Um, the units of Q over time are joules per second. So those are the SI units. Now, we don't know what K is, so I'm going to leave K by itself. And honestly, I don't remember what K is. I look at the equation and then I kind of figure out what K is. So I'm going to just step through that with you. The units of area is meters squared. The units of delta T, keep on writing that. It's either K or degrees Celsius. Now, as a reminder, if it's a delta, then those are the same. If it's a T, then it needs to be Kelvin. But if it's a delta, then you can use either. Okay. And then D, that is in units of meters. All right. So the idea here is that we need to have these units match up. Now, we do get one of the meters canceling. So basically on the right side, what we have so far is we have meters times Kelvin, or Kelvin meters, whatever that means. Now we don't want Kelvin or meters on the right side. We want joules has a meter in it, but we're gonna just put we're gonna keep joules per second. Now, the other thing that the units of this K need to do, it needs to cancel out the meters and the Kelvin. So the units are, you have meters and Kelvin, or again, degrees Celsius. So those are your units of K, joules per second, meter, Kelvin. And that's what gets the units to match on both sides of this equation. So that's kind of how you can figure it out. You want your units to match up. We could break the joules into Newton meters and then newtons into kilogram meters per second if we were so inclined. I think this ends up being kilogram meters per second cubed Kelvin if you do it that way, but it's typically represented in this fashion because it is a little bit more meaningful than just a purely base unit, because it does give you a sense of energy flow because it's measured in joules. So I wanted to quickly go through. Actually, I tell you what, I'm going to hold all the examples to the end. That way, if people just want to check out the examples, they can do that. But I've got a couple of examples for this that I want to go over, as well as for thermal expansion. But we will jump into thermal expansion for now. Okay, so thermal expansion, basically this is the phenomenon that all materials change size when temperature changes. Okay. Now an example of this that I kind of wanted to show you. So I want to show you a couple of pictures where this comes up. I need. So I'm gonna have to bring these pictures in another way. All right, so the first one, something you may have seen before, you may be familiar with, right here. This is a thermal expansion joint. And the idea here is that these are more common on bridges. Sometimes roads have them, but it's far more common on bridges. But the idea is that the materials that the road is made out of, it's gonna have to thermal expansion joint. It's gonna have to compensate for a variety of temperatures, which means it's going to, it's going to expand, it's going to contract. Basically, what this joint does, it kind of locks it together in this comb shape, so that when it expands, it has room to move, but it also has room to contract without sort of the road kind of slipping apart into different pieces. Now, you basically want this because, again, when it contracts, you don't want the pieces of the road to fall apart. That would be bad. But also, when it expands, you don't want them to start crushing into one another because it's kind of easier to see what happens with railroad rails if you get too much thermal expansion without enough room. But I'll show you that one as well. But this can happen with roads as well. So let's show this one. And maybe this one will come up. So what we have here is we have railroad bowing. So this is rail bowing due to thermal expansion. Now, the idea behind this is basically these rails, they started to heat up and they started to expand. Now, when rails are laid, they're typically given a little bit of room to thermally expand. It's possible this rail, somebody screwed this up, and that's why I did this. But what I think is more likely to have happened is that it got hotter on the rails got hotter than it was designed for. And basically what happens is they have a little gap between them. And if they start thermally expanding and they make contact, they want to keep thermally expanding as they heat up. Well, what ends up happening is the rail ends up bowing in a lot of different places because it's too long and the only place it can go is left or right. So you end up with these kind of weird patterns, these wavy patterns in the rail because of thermal expansion. Okay. So, and you don't want this to happen with the roads. Like you don't want the roads and the steel and the bridge to start bending. So you got to leave space for thermal expansion. That ends up being rather important. Okay. So that is what is going on with that. So that's thermal expansion. Now, I do want to talk about the formula. So yeah, go to the formula. There are two that we're gonna basically using or end up using. One is for linear expansion. Now, this tends to be for solid objects. Now, it's true that any solid object has 3 dimensions and it will thermally expand in all of those directions. But for something like a railroad rail, we don't really care how much wider the rail gets. That doesn't affect much. It's also quite small. We don't really care how much taller the rail gets. It's really how much longer the rail gets that matters. And so that is this linear expansion formula. And we define the change in length. Now, this is going to depend on 3 things. So we'll actually list those. Depends on. One is the original length. So we call that L0. So the idea here is thermal expansion is basically, it operates on a percentage of the material that's present. So basically a material expands by a certain percentage. What this means is that how much you have, how much absolute expansion you get depends on how much you started with. So this is the original length of the object. We also have a delta T, and really this is really the change from temperature, and it's the temperature of L0. Okay, so basically you have a reference length and a reference temperature. So whatever L0, whatever the temperature was at L0, that's your temperature, that's your reference temperature. Delta T is going to be how much you're different from that reference temperature. Okay, so it's not the absolute temperature, it's whatever the change is from, what the length was when it was L0. Okay. And then the last thing it's going to depend on is the material. Some materials are better at thermally, or some materials thermally expand more, some of them expand less. The symbol we use for that is alpha in this case, and this is what we call the coefficient of linear thermal expansion. Sometimes it's just called the coefficient of thermal expansion, but I like to remember that this is the linear case. And basically, the thermal expansion is just the product of these three things. So delta L is going to be equal to alpha L0 delta T. Okay, so that is how much you change by. Now, that's not going to be the new length of the thing. If you want the new length, you'd have to add L0 to your delta T. Okay, so that's going to be what's going on there. Now, we also have a volumetric expansion. And it's very similar. It's just delta V. This time it's beta instead of alpha, but V0 instead of L0, and then delta T. And this is just the coefficient, and this one is often called the coefficient of thermal expansion. But I like to call it volumetric thermal expansion. It turns out, for various reasons, that the beta ends up being approximately equal to 3 alpha for solid materials. For liquids or gases, there's really the really only one that matters is beta, because they're not rigid enough to have 3 alpha. That's approximately what it's equal to. But in any event, both of these things can be found. I believe it's section 13.3. You can find linear coefficients of expansion and volumetric coefficients of expansion. Okay. Now, when it comes to volumetric coefficients, like for solids, you have both a linear and a volumetric. Okay. Now this is particularly important if you have like a container made out of a solid that's holding a liquid. Okay. Now, if both of those things are heated up, both will undergo thermal expansion, the container and the liquid. Now, even though the container is basically just the shell of the solid, you can still use the volumetric coefficient of expansion. Okay, so that's something to keep in mind, comes up in a lot of these problems. Okay, so that's just worth remembering. Now, like I said, I think that's really it. That's all we need in terms of the equations. But I did want to go through a couple of these examples, like 4 or so. Okay, so some of them I'm going to change because I just pulled them from the textbook, and something we're not going to talk about everything in this chapter just because we don't have time. Now this one says a styrofoam box has a total area of 0.95 meters squared with walls and average thickness of 2.5 centimeters. The box contains ice, water, and canned beverages. The inside of the box is kept cold by melting the ice. How much ice melts in one day if the ice box is kept in the trunk of a car at 35 degrees Celsius? I'm not going to worry about this. This has to do with latent heat. Another thing heat can do to matter is it can cause it to change phase. Now, while that's happening, the temperature doesn't actually change. So that's where this concept of latent heat comes from. It's a little beyond the scope. It's not, I mean, it's something we could cover. We just don't have time to cover all of it. So I'm not gonna go into that. So I'm just gonna say how much heat is transferred. All right. So in this case, it's none of this is particularly bad. So we want to know, okay, what is Q? Well, that means we're going to need the coefficient of thermal expansion. And again, this is in section 14.5. You could just go look that up. 14.5 table. I'm sorry, thermal conductivity. This is not the thermal expansion. So this is how much heat is moving. So you do need to, that's the first thing you need to realize, that this is about heat moving. This is not about thermal expansion, and it's not about changing. So it's not about heat capacity either. It's about heat moving from the trunk into the cooler. So that means it's a conduction question. A, they give us directly, and they're nice enough to do it in SI units, so that's fine. D, the mistake here would be to say it's 2.5 because D is given in centimeters. So you do need to convert all these things to SI. Now, delta T, this is going to be the hot minus the cold. So it's just 35. And again, you could convert both of those to Kelvin, but if you did, you would still end up with a delta T of 35. So that's why it doesn't matter for this one. Now, the last thing we need to know is time. And this is 1 day. we do need to convert that to seconds. 1 day is 86,400 seconds. You can check that out. It's just 60 seconds per minute. So 60 times 60, 3,600 seconds per hour times 24 gives you 86,400. All right. And then basically what you would do is you would have Q over T, or you could even use the first equation. It's K A delta T over D. And then you just plug in. Okay. So really this is just about evaluating. Evaluating and finding Q given these things. And you could solve for Q first. You could, multiply both sides by T. But that's kind of up to you. Okay, so that's basically what's going on with this. I'm not going to run through that. I'll let you plug that in if you wish, but that's what's going on there. All right. Okay, so next one I wanted to look at. Whoops. So it says water is boiling in an aluminum pan placed on an electrical element on a stovetop. The saucepan has a bottom that is 0.8 centimeters thick. Why is it not here? Sorry, I was reading it on another. Oh, I think I know. There we go. Okay. Water is boiling in an aluminum pan placed on an electrical element on a stovetop. The saucepan has a bottom that is 0.8 centimeters thick. So I would start just writing things down. I can kind of tell that this is going to be a heat conduction problem. So I would make sure to convert it to meters. 0.8 centimeters, 0.008 meters. 14 centimeters in diameter. So that's going to give me an area. And it's going to be pi times 0.14 squared. Okay. So that's something we can find. So boom, boom, boom. The boiling water is evaporating at a rate of 0.1 grams per second. Now, again, this is actually a latent heat type of question. This is okay. So how quickly is heat being added to the steam and how quickly is it evaporating? And basically the idea is that what you could, in general, what you could do is you could use this to find Q. Now, again, we're not going to go into that. So I'm just going to say Q, really Q per time. So Q per time is going to be, I don't know, I'll just say 500 watts. So Q over T is equal to 500 watts. All right. And then it wants to know what is the temperature difference. So it wants to know delta T. Well, in this case, what we would do is we would have K, and again, this is from in table in 14.5. You can look that up directly. So that would be the K of aluminum, because that's what this pan is made out of. And then you just set this up. You just do Q over T equals K, A, and then I'll put the delta T over there. And then basically you just want to solve for this. Okay. And you can plug it, you can solve algebraically beforehand. I could just do that real quickly. That's going to give you QD over, well, I'll say Q over T times D over KA. Because Q over T is kind of one quantity right now. So, and then that's equal to delta T. All right. Now, again, both of these questions, the reason I picked them I picked them for examples because they were in the chapter, but we also didn't do any discussion of latent heat. So we can't really get to the Q in this case, or in the previous case, we can't. Yeah, we can find the Q, but we couldn't convert that to ice melted. If you want to check out those sections of the book, that's fine, but I'm not going to be asking questions on those. At least I don't believe I am. I'm pretty sure my homework questions don't do that, but I will make sure. Okay, so that is those are the two examples of heat conduction right there. Now, the next one I wanted to look at was thermal expansion problem. Okay. All right, so this one says the main span of San Francisco Golden Gate Bridge is 1275 meters at its or long at its coldest. Okay, so this is important that what we need to know is that this is basically saying L0 is equal to 1275, and then the T low is equal to, so T low, T sub L, negative 15 degrees Celsius. T high is equal to 40 degrees Celsius. I would just go ahead and calculate the delta T. That's going to be 40 minus a negative 15, which will be 55 degrees Celsius. And again, you could convert both of those to Kelvin if you were so inclined. Okay. Now, it does say the bridge is made entirely of steel. So it would be K sub steel. And then again, that's in table, I think it's 13.3. I think that's correct. But anyway, it's the section with on conductivity. Actually, I think it's might be 13.5. I don't remember. I'll leave it as 13.3, but it's a table. You can find that in your textbook. Okay. Now basically we want the change in length. And actually this isn't K anymore. It would be alpha. Okay. So this is change in length. This is linear coefficient. So it would just then be delta L is equal to the alpha of steel, which you would look up, times 55. That's your change in temperature, times L0, which is 1275. All right. So and I'll just rewrite the equation. Delta L equals alpha L0 delta T. Now I did flip those below, but it doesn't matter. It's multiplication, it's commutative. Okay. So no big deal on that one. All right. Now I do want to show you this this next one because there are a couple of issues that do come up with some of these. It's a short question. But it says suppose your 60-liter tank steel gasoline tank is full of gas. So both the tank and the gasoline have a temperature of 15 degrees Celsius. How much gasoline has spilled by the time they warm to 35 degrees Celsius? Okay. So what we want to do is we want to change the delta. We want to find the delta V of the tank. And we want to find the delta V of the gas. And basically we want to compare them. Okay. So we want to compare which change in volume is larger. Obviously, we think the change in volume of gas is going to be larger. But and again, I'm not gonna look up these things. You can go ahead and do that if you want. But then so the spilled is gonna be your change in volume of gas minus your change in volume of your tank. Okay. Now they're gonna have the same initial, which will be 60 liters. Now you may not remember this, but this is worth remembering because a lot of times volumes are given in liters, but 1,000 liters equals 1 meter cubed. Okay. So basically, this is going to be 0.06 meters cubed. All right. So that's your initial volume. All right. Your alpha, or sorry, not alpha. We want to use beta now. We do not want to use the alpha of steel. So we want to use the beta of steel because this volume is the change in volume of tank is going to be reflected in the volumetric change of steel, not the linear change in steel. And you can think about it this way, that what you're going to have is you're going to have the steel growing in 3 dimensions. So it's going to be expanding in 3 different dimensions instead of just one. And all those dimensions will be relevant. Okay. So, and then for the delta V of the gas, you're going to have the beta of gas. And again, both of these are in the thermal expansion table. And then your delta T is just going to be 35 minus 15, which is going to be 20 degrees Celsius. Your delta V of the tank ends up being, just do this in order. Beta of steel times V0 times delta T. And the delta T's are going to be the same for both cases. Your delta V of your gas is going to be your beta of gas, V0 delta T. And then your spilled, we could even, set up a subtraction, and turns out we could factor out the V0 and the delta T, and just going to be the difference between your volumetric expansion of gas and your volumetric expansion of steel. Okay, so that would be how you could solve these. Like I say, you can go look up these numbers and go plug those in, but that's going to be your basic approach. Okay, so I'm going to go ahead and end things there. That will be it for this lecture. Hopefully you will have what you need to work on the assignment that when we have these things. And please go ahead and ask me for questions if you're confused about anything.